You already know about the structural gate level modeling from last episode. This method is good for small digital circuit blocks. For bigger and complex blocks, you need to change your method to data flow modeling in Verilog. Design equations are formed to replicate the physical data flow from input ports towards the output ports through data flow modeling. Equations are very easy to grasp and write. So let's start our learning journey for the data flow modeling in Verilog.
Hey guys, welcome back. In today's episode, we are going to discuss the below points. We'll give an overview of the Verilog modeling methods. Next, we will give our introduction towards data flow modeling in Verilog. Next, we will talk about the significance of continuous assignments in data flow modeling. Next, we will do the data flow modeling of a half adder in Verilog. Next, we will do the creation of the test bench of the half adder, which has been designed through the data flow modeling. Next, we'll do the code simulation with the combination of Geany IDE, Icarus Verilog and GTK-Wave. Next, we'll do the code simulation using Vivado 2022.1 ML edition. So this way, you will have both the taste of Icarus Verilog as well as Vivado for the Verilog code testing. That's the menu for today. So without any further delay, let's begin. Verilog modeling methods. We can divide the different modeling methods in Verilog in two major types. The first one is the structural modeling, which is done using the gate primitives, and the behavioral modeling, which is done in two different ways. The first one is the continuous assignment. We use continuous assignments to do the data flow modeling, and the procedural assignments. This is another way where we use the if, else, etc. different things and all these blocks here in the procedural assignments. In today's episode, we will talk about the continuous assignments, how we do the data flow modeling using the continuous assignments. This is a brief overview of the Verilog methods. We are done with this particular slide, so without any further delay, let's move on to the next slide. Introduction. Small digital circuits can be easily described by structural or gate level modeling. In last episode, we have done the structural or gate level modeling. For large or complex circuits, it's easy to use the logic equation at coding or programming level to describe the nature of the flow of data in the circuit. Now, we are doing a level up here and we are moving towards a bit large and complex digital circuits in nature. There, the method that we will use is the logic equations at coding or programming level. This one. And also keep the point here, the flow of data. That means we have a circuit right here and we have some inputs here and outputs, and flow of data means obviously data will flow from this towards this direction. So this is the data flow. The word data flow means this kind of operation which is shown by this diagram. Data flow modeling describes the architecture of a digital circuit without describing the explicit components, rather describing in terms of the flow of the data from input towards the output. You are very much aware that in last episode, for structural modeling, we have used the gate primitives and we have interconnected the different gates to construct the circuit, where our circuit was already ready by the Carnot mapping and POS or SOP form in hand. However, the data flow modeling, which is a bit different here, the data flow modeling is different. So you have to design the data flow. That means this is a circuit and we have inputs and outputs, and data will flow through the circuitry towards this point or towards this point. So there will be lot of circuitry here. All these equations which will help the data to propagate from the input port towards the output port is the technique called data flow modeling. And here we refrain from expressing the exact digital circuit with explicit components. Here we have used the explicit component, that is the gate primitives in structural modeling. Here we use equation, but we refrain from using the gate primitives. Rather, we have logical equations to build up the data flow. However, we will have a test bench to testify our own design, which in every episode I essentially include, because otherwise your design is untested and you don't know what can be the output. Dataflow modeling uses continuous assignment to code the above mentioned equations. Now, we have done the structural modeling where we have used the equations to interconnect the gates, and in Dataflow modeling, what we are doing, we are using continuous assignments. In today's example, I'll be using the continuous assignment, which is nothing but a assign statement to code the above mentioned equation. So that means the data flow. So we have to create the data flow using logical equations. These are logical equations rather than explicit equation in terms of gates. These equations may contain one or more operators among the arithmetic, logical, conditional, relational, equality, bitwise, shift, reduction, and concatenation. So let me clear it. So the equations that we are going to form the data flow, we will construct the data flow from in to out, will include some of these mentioned type of operators. So there could be arithmetic operator and conditional operator. There could be relational operator. There could be only bitwise operator. There could be shift operator. There could be concatenation. We will use different combinations of all of these operators in Dataflow modeling. However, in today's episode, the example is very short and simple. Just to begin your Dataflow modeling, later episodes we may come up with a complex circuit where we are using different kind of operators. So we are done with this particular slide. So let's move on to the next slide. Continuous assignments to be used inside Dataflow modeling. How do we use the continuous assignments? Here are some glimpses for you. Dataflow modeling is used to represent the code or combinational circuitry. A net is assigned using the continuous modeling with a assign statement. Let us begin the examples. These are not code examples. This is the example of the assign statements for Dataflow modeling. First, we can define where type net with 3 down to 0. We read it like 3 down to 0. This is a bus, and preset and clear. And we end the statement with a semicolon here. Next, we use these variables which we have defined here using the where statement to construct the assign. We have defined the variables here, and here to represent the data flow, we will use this equation. Here the statement name, this is a reserved keyword. Assign is a reserved keyword, and hence here it is shown in green. In a particular text editor, it may come up with a different color. However, this is a reserved keyword. You cannot use it for your own variable name or any other personal purpose. So it is assigned for a particular function, and here it has to be used. So here you can see the equation Z, this one is AND, logical AND of present and clear. Here there is a typo here. So this is a preset, and there is a typo. It has become present. Please excuse me for that. So Z is nothing but the AND form of preset and clear, which we have defined here and here. So next one, expression on the RHS is evaluated whenever any operand changes its value in the RHS. So whenever the preset or the clear changes a value, assign statement keeps a track of this change in any of these variables, and whenever there is a change in either preset or clear, the entire equation is evaluated at that particular time point. So at maybe time t equal to 10, this is evaluated. Time t equal to 20, it has happened again, there is a change, so it will evaluate again, and hence it will go on. Next, we give another example. Here we define a net using where, that is C out and C in. These are two different wheres, that is nets. We define a couple of more wheres here. 3 down to 0 sum is a bus, and A and B. Next, we use the assign statement here, assign, hence it is in green. And here you can see this curly brace, right? This is a concatenation operator, right? Here it concatenates these two. And here we use the logical expression of ORing, that is A or B or C in. So this is a logical ORing operation, and this is not a regular addition operation. This is a logical operation here of the ORing, and hence the assign statement, the entire assign statement creates a relation between the inputs and outputs. These are outputs and these are inputs. So this way the data flow is modeled by the assign statement. Here is also it is same, these are inputs and this is output. So you can see that the assign statement can be used to model the data flow from input towards the output. So arrow is going in the left hand side, and here is also from input towards the output, and here the arrow is in the left hand side. From right hand side it is evaluated and the value is assigned at the left hand side. So data flow here for a circuit here, right, when we draw like the in is here and out is in the RHS, right, this is in and this is out. So in and out is here, right? However, when we are drawing, right, we are drawing from left to right here. The flow is going. However, in equation, you can see it is going from right towards the left. From right towards the left. However, in the circuit, when we are imagining the circuit, the data flow is from the in to out, that is from left towards the right. So keep this thing in mind. In continuous assignment of data flow modeling, LHS, that is the target, is a expression, can be a single net, that is Z, bus, that is a bus which we have already encountered here, the sum one, then the bit select, right, a single bit. Z is a 4 bit, right, 3 down to 0, and here Z we can assign one single bit also. Let me clear the drawings here. Z1 can be assigned. This one can be assigned individually 1 bit by any operation which we have discussed in last slide. Be any type of operation, and with the assign statement we can assign this. Next, we can use the concatenation. I have already mentioned here. Here it is already the concatenation I have shown you, and this is a good summary. Here it could be a single net, it could be a bus, but bit select, and here it was a part select, that sum 2 down to 0. Part means not the whole. Here sum is 3 down to 0, and here we have used only 2 down to 0. So it's a part select, or it could be a bit select, a single bit, or the entire bus could be used in assign statement. So this way we can have many combinations of the assign statements to describe the data flow as per our design, or the design and the design need. So here we are done with this particular slide. Let's move on to the next slide. Data flow modeling of a half adder. So here we'll do the Verilog coding of a half adder for the data flow modeling. Here goes our comment, half adder circuit, and we start our module definition. Module half adder, we name it, and we give the A, B, sum and carry, right? So these two are inputs and sum and carry are the outputs, right? So here you can see our circuit, and as I was saying, in the design of the circuit, generally we draw that our inputs are at the left while our outputs at the right. So A, B, sum and carry, and this is a block diagram. So here the A is in upper caps, B is in upper caps, sum is in upper caps, carry is in upper caps. And when we are using the nets, right, we are using them, or the sum or carry, right, these are ports here. So we define these two as inputs with this input command, and we define output and type is where, right, for the sum and carry. So this sum and carry we have defined as outputs. So these are inputs and these are outputs, right? So this way we define the in and out with these two statements. Next, we are using the assignment statements, that is the data flow modeling. We define sum is equal to the A XOR B. We know from the basic equation of the half adder, right, that A XOR B, this sum is nothing but A XOR B. So here the caret sign, that is this sign, is equivalent to the XOR sign here. So you have to remember these mappings, right? Otherwise we don't have a exact XOR sign here. We used to use the caret for the XOR sign. Later I will give you the different operators which we will use in tabulated format in some other episodes. And the carry is A and B. So this AND is a logical AND. This is a logical AND. So this is nothing but the AND operation, logical AND operation, not the AND gate. So here you have to be very careful. This is a logical AND operation and this is a logical XOR operation. However, the symbol is different here, and in some later episodes we will cover all of them through the tables. And here we end our module of a half adder. Here you can see that we have used the data flow modeling of Verilog to construct the data flow from the input ports towards the output ports here to the assign statements. This is the data flow modeling in Verilog. So we are done with this particular slide. Let's move on to the test bench. So here we will design the test bench of the half adder which we have done through the data flow modeling. Now here, let me tell you one thing. We are not using the Dataflow modeling for the test bench. The test bench is a common practice that you will become familiar with multiple examples throughout this series, and you will be very easy after a couple of episodes to write your own test bench. So here we name that test bench here test bench half adder, because you know, right, our test bench is nothing like the compared to the breadboard, which do not have any ports, and there we instantiate a module which is nothing but in actual breadboard is a chip which has ports. The module which you have defined in earlier slide had input and output ports. However, here, since this is a test bench, nothing but similar to the breadboard, it do not have the ports. So we do not have the ports here, only a empty brace here. So here we give a picture of the module which we are going to instantiate for our ease. Now let us define the range A and B. Range is nothing but it has memory. This kind of nets has memory and they can remember the values over the time period. That means because our Verilog simulation is a transient simulation and we do the simulation with respect to the time. So these register variables have a nature of remembering the data values over time, because in Verilog the simulation happens in the independent axis there is time. So time goes in the independent axis and the rest of the variables will change in the y-axis. So here we will have multiple things, but however the x-axis it will be time. Over time, if we have to remember some values, we have to use the range kind of nets. Then we use the where, sum and carry, and we start our initial block here. Then we write the first statement inside the initial block as dump file, and here we give the halfadder.vcd, this name. So this file will be dumped, which we can view in the GTK-Wave. Next we give the dump var. So this dump var does nothing but this dump var, what it does, it captures all the changes on all of these variable and time t and dumps them, all of them inside this file. These two has to be used back to back so that we get the filled up VCD file. So we use a printf statement just for the heading print here, checking the output of the half adder. Then we give the another heading. Here we have a tab separated. First one is the time because it's the independent variable, then A, then B, then S, then C. That is S is sum and C is carry. And here we give a monitor statement which is very different from the display. Display is a static print and it occurs only one time. Wherever the monitor is different, because it keeps on monitoring all of these variables. If any of them changes at a particular time, right, the monitor gives the print on the screen. So this monitor statement will fill up the column values of time A, B, S and C. Here you also see it is tab separated. And here we have explicitly given time A, B, sum and carry. So this way it is filling up the output columns. Now here, you know, this is a delay element. So at time 0, we give the value here. Let me tell you again one thing. This is a shorthand. If we use this thing, this curly brace, and we club the A and B two variables together, that means the two inputs, right? We are clubbing here and we use 2. 2 means the width is 2 here, 2. B is binary. Tick we have to use. This is the convention, and we give 0 and 0. That means 0 to A and 0 to B. We assign these two values. We do not use assign statement here. We are just giving the values or changing the variable values using this particular statement. And here you can see, right, we have changed the value here 1, and this is after 5 time unit delay, and this is after 10 time unit delay. We have changed it to 0 and we changed it to 1, and here 1 and 1. You can see for A and B, for these two inputs, we have defined the truth table for the input change, and we will get the truth table output for sum and carry to the printf statement in the screen. Here at 20 time unit, we do the finish. This finish keyword finishes the simulation, and it finishes the time-wise simulation at this after 20 of this. So when we add 0 plus 5 plus 10 plus 15 plus 20 equal to some time units. At that time unit, the finish will occur. We end our initial block here with this end. And then we instantiate our half adder module using the half adder, and we give the instance name as HA, and we give the ports names A, B, sum and carry. Already we have defined the types. It is range and this is where, right? here you can see that we have connected these ports in the instance. Another thing here, let me tell you, this range will remember over time. So whenever we are moving from 0 to 5, these values will be retained up to the 5 time unit, and after that this will be changed. So range is the purpose, because here A and B has to hold on to the value here. Outputs are where, so they will simply give the output. However, these inputs have to be memory type. That means they have to hold on to the values of 0 and 1, 0, and they has to change up to 1 when after 5 time units, and from this to this move after 10 time units, from 5 to 10 they will hold this value, and then it will changed by this statement. So this is the significance of the range type of net, and here we end our module using the end module statement, and here we end our test bench. So that's the test bench. We are done with the test bench, and let's move on. Hey folks, we are in the folder where the Verilog code is kept. Let me open a terminal here, and let me open Geany. Folks, you can see here the module half adder which we have just talked about is written here with its inputs and outputs. And here in Geany you can see the reserved keywords are highlighted in deep blue or navy blue, whatever you can say. And we have the test bench here. You can see the test bench is written here with the inputs and outputs for the instance here. And we have the truth table input combinations defined here, and the outputs will come to the screen using this print commands. These are display and monitor, two types of print commands. Monitor is a dynamic print command and the display is the static print command. So let me here do a ls halfadder.v. Let me run the code through the iVerilog, that is the Icarus Verilog. So we have typed the simulation command iVerilog halfadder.v-oha. So the output object dump will be named as ha instead of the default a.out. The simulation, here you can see the object dump is created ha, and let me run the object dump. And here you can see the comparison. Here we have defined the time A, B, S and C using this particular display command, and the values for all of these changes here, this change is depicted here using the monitor command, and the output for the sum and carry are depicted here. So you can see the truth table has been printed here, and here we also can see this time values, the time values which you have given with the hash statement. Here you can see that these time values are also printed for the time. So this is a time wise simulation, that's why. And by your basic common sense you can understand this is the truth table of a half adder. We have verified our design which we have done right in the Verilog modeling using the Dataflow assigned statements is correct, and the output is giving correct, which is verified by the truth table. Let me open GTK-Wave. Sorry folks, there is a typo, let me correct it. GTK-Wave, and let me launch it once again, and here it has launched. You can see here the test bench is there. Inside we have the half adder, right? Half adder instance named HA, and let me expand it, and this is the first two inputs, right? And then we have the sum and carry. Here with this button we are doing the fit screen, and if you do the values here, right, AB00 sum carry 00. So here change 0110, and here 1010, and here 1101. So this is the basic truth table. Also you can find from the graph. You have to just point the marker here by clicking directly on the graph on the right hand side. Here I think we are done with the graphical verification of the half adder that we have, and let me close it. So here we are also done at the Geany front. And here we will open up Vivado. Let me open the Vivado. So it is opening up. You can see the Vivado 2022.1. This version is opening up. So here it is starting the GUI. You can see the message, and here the splash screen has come up. Now our interface of the Vivado is here, and let me create a project. It has picked the directory name correctly here from where we have launched it, and we have checked the option create project subdirectory. So we have clicked it, and here we are selecting the RTL project and do not specify the sources at this time. So this we are picking up. Next, and here it should be all, everything is all right, and we go to the board and click on to a board, and then we click next. So it gives some message which, so let me close this website. It has taken to the board definition and all. So it has given the new project summary here. Okay, our new RTL project will be created, and we have picked up the board. Although here we are not using the board, we are doing just the simulation, so it's okay with us. Let us click on finish. I will go for this add sources now, because we have written the Verilog file here with the module and the test bench inside the same file. From the directory we have launched the terminal, and through the terminal we have launched the Vivado. So we will go and click on the add sources. So we will pick up the add or create design sources, this option, and next we will go for add files. So in this particular folder we already have the half-adder.v which we are picking up, and here is the preview of the file. In case you have multiple files, you can check the preview here, and we click on OK. So here we click on finish. So here you can see the half-adder.v. It is opening in editor. So here you can see the module definition is getting displayed, and if we scroll down right, the test bench is also displayed. So we have opened the correct file here, and now let me go for the, we will go ahead and click the run simulation here at the left, and we will pick up the run behavioral simulation. So the simulation has finished. This is a graphical form, and let me open the text form here. So I have resized here. So here you can see the output here. So these print commands, the display and the monitor commands, help to print out the two top lines where the definition of the output and the column names have been described. And here you can see these time values which are simulated has come here with the print command here, the monitor command, and these change of the input values for A and B, these have been displayed here. However, there is a shift here. You can see for A this line is picked, for B this line is picked. Okay, now the output has been displayed here for the sum here and the carry. So there is a shift here due to the white space management of Vivado during the print commands. And you can see, however, here it has been, if this is the sum, right, so this is a XOR of these two only. It is 1 only when 0 1 and 1 0 combination, that is exclusively either A or B, any one of them is 1. The sum has been truly evaluated, and for the carry it is AND, that is A and B. So here you can see these three are 0 and only this is 1 when both are 1. The truth table has been correctly displayed here for our module under test. So here let me resize it and let me shift it a bit, and here we use the zoom fit command similar to the GTK-Wave, and here you can see we are having the binary values here. Now let me click here. At the beginning you can see 4 are 0 right here, then here 0 1 1 0, and then here if I click 1 0 and sum and carry will be 1 0, and here 1 1 and it is 0 1. So this way, if you just try to probe by clicking here, here, here and here at 4 points, you will get the corresponding binary values from where you can construct the truth table for the input and output, that is A, B and sum and carry. So the truth table is also correct here to the graphical form, and here we are done. So here we will end our episode, and thanks for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, put that as in words in the comment section down below, and bye for today.